This is our cloud-native e-commerce platform built entirely on AWS. What you are seeing right now is the customer-facing storefront. The front end is built with React and Vite styled using Tailwind CSS and served through an Nginx web server that handles all client-side routing, redirecting every path back to index HTML, so our application works seamlessly. In front of that, we have an AWS application load balancer, the entry point for all incoming traffic. It distributes requests across multiple availability zones, ensuring no single point of failure brings the platform down. The homepage itself showcases fashion catalog, products for men, women, and kids with a clean, modern design. Users can shop directly, view offers, or browse the full collection. Notice the login button in the top right corner. Authentication is handled entirely by our dedicated user service. When a user logs in, the service verifies their credentials using bicrypt password hashing and issues a JWT token. We also support Google authorization for a faster one-click login experience. That JWT token is then validated at the API gateway on every single request before anything reaches a backend microservices. The gateway decodes the token, extracts the user identity, and injects it as a header to all downstream services. This means no service ever needs to revalidate independently. Security is enforced at one central point. In here, user can log in into the website using their email and the password, or they can log in with their Google accounts. After login, this is admin login. This is the admin panel. Here the admin can add new product, entering the product title, regular price, offer price, and selecting a category such as men or women. Product images can be uploaded directly here from your devices, and you can add product, then product is added to the product list. This is the product list view. The admins. Now let's look at the customer experience. After login, a customer can browse a product catalog, shirts, frocks, long frocks, each showing both the original and discounted price. Clicking on a product opens the detail page where the customer can see the item image, rating, price and size options, small, medium, large or extra large. From here, the customer can either add to cart or buy it now. This is the cart page. The item has been added. One shirt at 2,800 rupees. The cart is powered by our cart services. Inline editing allows price updates directly in the table. Here you can see successfully edited the price. Then here you can see price being changed and saved in real time. And also products can also be deleted with a single click. Every one of these operations goes through the product service REST APIs. And here you can check out the product and buy the product using these filling options. When the customer clicks checkout, a strip payment model appears. Strip elements collects card details securely and PCI compliantly on the client side. This is how we guarantee our 99.9% uptime target and catch problems before they ever reach the customer. That concludes our live demonstrations of cloud-native e-commerce platform, a scalable, secured, and highly available cloud e-commerce platform. This is the overall system architecture of Sihaya. Client request from the web front end and admin panel flow through an Nginx API gateway which handles authentication and routing into our 5 core microservices: user, product, cart, order, and payment. Each service connects to its own database: MongoDB for user, product, and order data, Redis for the cart cache, and RabbitMQ for asynchronous order and payment events. On the infrastructure side, we use AWS VPC, an application load balancer, and EC2 instance to host our containerized services. Originally, we planned to use EKS, Elastic Kubernetes Service, but the EKS is not free of charge. We opt for EC2, which gave us full control at a significantly lower cost. For DevOps, we use a GitHub Actions CI/CD pipeline with Terraform for infrastructure provisioning and Prometheus with Grafana for live monitoring across all services.
Alright, let me talk about our microservices architecture. We broke down the entire e-commerce system into 5 separate microservices plus an API gateway, each doing one specific job. So this is a key part of being cloud native. Instead of being one big monolithic application, we have small focused services that work together. So we'll go through one by one about microservices. We have 5 microservices. The first one is we have the user service. Here we have the user service, and this handles all user related stuff: registration, login, user profiles, and user roles like customer or admin. It uses MongoDB to store user data and bcrypt for password hashing. So we never store plain text passwords. So when someone logs in successfully, it gives them a JWT token that lasts 24 hours. So this token is used to authenticate all their subsequent requests. So here, this is the user model schema in MongoDB. So you can see we have fields for name, email, and password, which is hashed with bcrypt, role for access control, and Google ID for auth support. The password is required only for local users, not for Google sign-in. So next service is the product service, which manages the product catalog, all the products, their categories, prices, inventory levels, and product images. When someone browses the store, this service provides all the product data, and it stores everything in MongoDB because products can have different attributes, and like clothes have sizes but electronics have specs, and MongoDB handles this flexibility really well. And here in product service, this is the models file where notice the attributes field uses MongoDB's mix type. This allows products to have completely different attributes, like clothes can have sizes and colors, while electronics can have specs like processors. Electronics can have specs like processor and RAM. MongoDB handles this flexibility perfectly. So this is the model schema for product service. And then we have cart service. Here's a cart service. This is where we store shopping cart items. What's special here is we use Redis for cart data, and Redis is incredibly fast, like sub-millisecond fast for reading and writing. Each user's cart is stored as a hash with items and quantities. So we set carts to expire after 7 days, so abandoned carts get cleaned up automatically. Before adding anything to the cart, it checks with product service to make sure the product actually exists and it is in the store. So here is the code. And this is the code showing Redis components, and we use Redis client to get cart data with the key based on the user's email, and then set it back as JSON. Redis handles this in constant time regardless of data size. So the card key format is use@gmail.com for easy lookup. And this is the code for that. And next we have order service. When someone places an order, this service creates the order in MongoDB and with the status of pending. But here's the cool part is it doesn't wait for everything else to finish. So it immediately publishes an event to RabbitMQ saying order is created and returns success to the user. So other services pick up that event and do their work asynchronously. So payment service processes the payment. Then here is the code for order service. This is the model schema. This is the order model showing the order structure with items array, total amount and status. And here's the code where we publish order created event to RabbitMQ after saving the order. So this asynchronous pattern is key to our Saga choreography. And next we have payment service. This handles the Stripe payment process. When it gets an order event, it creates a Stripe payment intent on our server and gives the front end a secret to collect card details. So Stripe processes the payment securely and we get a webhook back confirming if it succeeded or failed. So we use idempotency keys if something fails and retries. We don't accidentally charge someone twice. So after payment is proceeded, it sends an event back to RabbitMQ so other services know the payment status. So payment service doesn't use its own database, it relies on Stripe and for payment data and communicates with other services through events. So this is the code for payment service. Here we have. So this shows how we create a Stripe payment intent. We pass the amount currency and idempotency key to prevent double charging. Stripe handles all the PCI compliance and security, so we never see or store actual card numbers. Then we are using Saga choreography for async communication between services. We use Saga choreography with RabbitMQ. Order service publishes event when orders are created and other services like payment services consume these events to process payment asynchronously. This decouples our services and makes the system more resilient. So next about API gateway. In API gateway, we run it on port 3000 and it acts as the front door for all requests. It handles JWT authentication, rate limiting and routes requests to the appropriate microservices. So every incoming request goes through the gateway first. And these are the things about all the 5 microservices plus API service about API gateway. And when we are talking about single responsibility principle, here each service has one clear job. This makes the system easier to develop, test, deploy and scale. For example, if many users are adding products to cart during a big scale, we can scale only the cart service without scaling the full system. So if the cart service needs more resources, we give it more. If order service is slow, we can scale that one. This targeted scaling saves resources and money compared to scaling the entire monolithic application. About database strategy, we use different databases based on the need. MongoDB is used for flexible data like users, products, and orders. MongoDB doesn't require fixed schema, so we can easily add new fields to products or orders without breaking anything. It's perfect for this kind of data that involves over time. And we use Redis for cart data because it is very fast. Cart operations happens constantly. People adding items, removing items, updating quantities. Redis handles this with one operations, which means constant time regardless of how much data you have. We also use Redis for caching sessions at the API gateway, so authentication checks are super fast too. And these are all about the 5 microservices.
Now I'll explain how our microservices communicate with each other. As you can see in our system architecture diagram, we implement both synchronous and asynchronous communication patterns. For synchronous communication, we use REST API through our API gateway. When a user browses product or add item to cart, the frontend makes HTTP requests to the API gateway, which routes them to the appropriate microservice. This is ideal for real-time operations where immediate response is required. For asynchronous communication, we use RabbitMQ message queue. This is crucial for order processing and payment handling. When an order is placed, the order service publishes an event to RabbitMQ and the payment service consumes this event independently. This decouples our service and ensures reliable message delivery even if one service is temporarily down. Let me show you how synchronous communication works in our code. Here in our API gateway, we use Express.js with HTTP proxy middleware to route requests. For example, when a user requests product, the API gateway receives the request at port 3000, authenticates with the JWT token and proxies it to the product services at port 3002. The product service requires MongoDB and return the data back through the same path. This pattern ensures single entry point for all requests, centralized authentication and authorization, load balancing across service instances, and consistent API version. For asynchronous communication, we use RabbitMQ. Let me show you the RabbitMQ management interface. Here you can see our message queue. When an order is created, the order service publishes a message to the order queue. The payment service listens to this queue and process management independently. This event-driven architecture provides loose coupling between services, reliable message delivery with acknowledgements, ability to handle high traffic spikes, fault tolerance like message persist if consumer is down. Our deployment on AWS EC2 uses Docker Compose for containerization, while we have Kubernetes manifest for production. For this demo, we are using Docker Compose, which is easier to demonstrate. For scalability, we configure service replicas in Docker Compose YAML. Each service can run multiple instances, and Docker's internal load balancer distributes traffic across them. For high availability, we use MongoDB with replica set for database redundancy. Services are stateless. It means any instance can handle requests. And also Docker Compose restart policies ensure service recovery and automatically. And also health check monitor service status and restart failed containers. In production with Kubernetes, we would use horizontal pod autoscaler to automatically scale based on CPU and memory usage. Then we will move on to the security implementation. Security is critical in microservices. We implement multiple layers. Like first one is JWT authentication. When user login, they receive a JWT token. This token is sent with every request and verified by the API gateway before routing to the service. The second one is role-based access control. Users have either users or admin roles. Admin users can access the admin panel, add admin to manage products. Then third one is the rate limiting. The API gateway implement rate limiting to prevent abuse and DDoS attack. Then fourth one is the course configuration. We configure allowed origin to prevent cross-origin attack. The fifth one is the secret management. This means sensitive data like database password and API key are stored in environmental variables, not hard-coded in the code. For authentication, we also support single sign-on using Google Authentication. Let me show you the login page with the Google sign-in button. When user click the sign in with the Google, they are redirected to Google's authentication page. After successful authentication, Google redirect back to our application with an authorization code. Our backend exchange this code for an access token and user profile information, then creates a JWT token for our application. This provides a seamless user experience while maintaining security through Google Authentication Protocol. Now let me show you the live demo. First, let's look at Redis, which we use for caching card data. I'll add the product to the card. In the front end, you can see the card data is stored in Redis for fast access. Redis provides sub-millisecond response times, which is crucial for card operation that need to be fast. Redis also handles session management, storing user session data for quick retrieval. For monitoring, we use Prometheus and Grafana. Prometheus collects metrics from all our microservices. Each service exports a metrics endpoint with performance data. Let me show you the Prometheus interface. Here we can see the metrics like request count, response time, error rates, and resource usage for each services. Grafana provides beautiful dashboard visualizing these metrics. We have pre-configured dashboard for service performance, resource utilization, business metrics like order and revenue, error tracking. This real-time monitoring helps us identify issues quickly and ensure our services are performing optimally. That covers communication method, scalability and security in our microservice architecture. We have seen how our services communicate synchronously via REST API and asynchronously via RabbitMQ, how we scale using Docker Compose replicas, and how we secure our application with JWT authentication and rate limiting. Now another member will explain our DevOps practices, CI/CD pipeline, AWS EC2 deployment, and provide a live demonstration of the complete application. Now other member will explain our DevOps practices.
In this section, we will cover the DevOps setup, containerization strategy, CI/CD pipeline, Kubernetes design, Terraform infrastructure, and our live AWS cloud deployment of the Sihara e-commerce platform. And here first we containerized every microservice using Docker. Each of our 6 services has its own independent Docker file, as you can see here, and each Docker file follows security best practices. We run containers as an unroot user called Node.js to minimize attack surface, and we use Alpine-based Node.js images, which are significantly smaller and have fewer vulnerabilities than standard images. Each service also exposes a health endpoint that you use to monitor container health. So here we use Docker Compose for 2 purposes. First one is for our local development. So Docker Compose allows any developer to start the entire platform with a single command, Docker Compose upd, and it runs all our 6 microservices. And second, we use Docker Compose for our actual AWS EC2 cloud deployment, which I will show shortly. So now we go to the K8s folder, deployment subfolder with all the YAML files. For production grade container orchestration, we designed and wrote complete Kubernetes manifest here. In the K8s folder, you can see deployment files for every service, as you can see in the screen.
And we also have namespace, config maps, secrets, infrastructure and services configurations as well. So each Kubernetes deployment is production ready. Here you can see the API gateway deployment running 2 replicas for high availability with CPU and memory resource limits defined. It has a liveness probe that restarts the container if it becomes unhealthy, and a readiness probe that ensures traffic only goes to ready containers. So here we must be transparent about something, that these Kubernetes manifests were designed, written and validated in CI/CD pipeline but were not deployed to a live cluster. This is because it would cost money to do it in AWS. So as students, this is not feasible for us. Our Kubernetes manifests are validated in our CI/CD pipeline using kubectl dry run on every push. So next, let's go to see the Terraform folder. We also wrote complete Terraform infrastructure as code for AWS. The main TF file provisions the entire cloud infrastructure, VPC with public and private subnets, and EKS Kubernetes cluster, RDS PostgreSQL for the user service, and like that. Again, also this Terraform code was written and designed, but Terraform apply was never run because provisioning this infrastructure would cost money. Now let's go to our CI/CD pipeline. We have designed, it is fully implemented and actively running using GitHub Actions. Every push to the main branch automatically triggers the entire pipeline without any manual steps. So as you can see, our pipeline has 7 stages, and stage 1 runs tree security scanning, which scans our entire code base for known vulnerabilities on every single push. And in stage 2, it builds and tests all 6 microservices in parallel using a matrix strategy. And stage 3, it builds Docker images. And stage 4, it builds the front-end Docker image. Stage 5 validates all Kubernetes manifests using kubectl dry run, and that is how we ensure our K8s files are correct without needing a live cluster. And in stage 6, it validates Docker Compose, and finally in stage 7, automatically deploys to our AWS EC2 server. So in the deploy job SSH into our AWS EC2 instance, pulls the latest code from GitHub, stops all containers, clean up and starts new containers. So this is true continuous deployment. Every push to main automatically updates the live site. So now let me show our actual live cloud deployment. We are connected via SSH to our AWS EC2 instance, and here you can see our Docker containers running on AWS. We deployed the core services on this EC2 instance because of the memory limitage of the free tier, which limits how many services we can run simultaneously. And the remaining services are all implemented and run on the full local Docker Compose setup. So the EC2 deployment demonstrates real cloud deployment using the same Docker Compose approach. And here is our live CR platform running on AWS EC2, accessible from anywhere in the world. So this is the platform and the React front end, as you can see here. So I'll demonstrate the authentication flow. Like you can see, we can log in and sign up and authenticate it to the website, as you can see in the screen. So the request goes from the React frontend to the API gateway on port 3000, and the user service validates credentials against MongoDB and returns a signed JWT token. All subsequent requests use this token for authentication here. So the API gateway is our single entry point here, and it handles authentication, verification, and routing to the correct microservice. So this is the standard cloud native API gateway pattern used in production systems as well. So in conclusion, our CR platform demonstrates all core cloud computing principles, and we decompose the monolithic application into 6 independent services, each with its own database following single responsibility and loose coupling principles. So in every service, it runs in Docker containers with security best practices. Docker Compose handles both local development and cloud deployment here. And our Kubernetes HPA configurations automatically scale services between 2 and 5 replicas based on CPU and memory metrics. And the stateless service design means any service can be scaled independently. Also, Kubernetes deployments run minimum 2 replicas per service with liveness and readiness probes for automatic recovery. As for the security, JWT authentication by crypt password hashing, trivial vulnerability scanning in every CI/CD run, rate limiting, cause protection, and Kubernetes secrets for sensitive data. So in conclusion, we can say that we hope we successfully transform a monolithic e-commerce application into a scalable, secure cloud-native platform that demonstrates modern cloud computing principles. Thank you.